Well, hello everybody, and welcome to our live stream of our tour of the universe. My name is Jackie. I am the manager of planetarium programming here at the California Academy of Sciences. I'd like to thank everybody for joining in and watching from all around the world, including our friend in the UK. You're still up late at night, and we appreciate you watching and tuning in. So we are going to be using a software called OpenSpace. It's an open source planetarium software that is funded by NASA. And in fact, if you are interested, you can download this on a gaming laptop or a computer and explore the universe yourself, just like we are today. So we are going to start our tour of the universe relatively close to home. We are going to start at the International Space Station. Now, the ISS, for short, is as far as humans do travel out into space nowadays. We can fit about 6 astronauts on it at any one time, and it is the largest thing that has been built in space so far. It's about the size of American football field, or I like to say the Academy of Sciences. So if you've ever been in our building, if you've walked from one side of the Academy to the other, from one garden to the next, you have actually walked the length of the International Space Station. Now, not all of the space station is used by humans. In fact, we have the solar panels that help give it energy. And where you see those kind of round tubes, that is where humans do live on the International Space Station. But today we are actually going to go much further from our planet. We are going to see how far our human influence has gone. We'll see how far humans have physically traveled. We'll see how far spacecrafts have gone and how far human communications have gone as well. But for now, the ISS is as far as humans have traveled into space. Now it looks like it's plummeting to Earth, but that's because we are zooming out. And as we zoom on out, I'm going to go ahead and bring up the path of the International Space Station. So we can actually see that path orbiting around our planet, and it's actually traveling quite quickly, about 90 minutes to go around our planet Earth. In fact, you can actually see the ISS pass overhead at night. Just look up online to see exactly what time of day it's going to pass over your area. And when you are looking up out in the sky, you're going to be looking for something that looks like a very bright star, but is moving very quickly. So now that we actually see our Earth from space, one of the really cool things about OpenSpace is that it is constantly bringing data in. And so we are looking at how the Earth looked yesterday at this time. If we wanted to speed time forward, we could see what it looked like today. Or if we want to go back in time to a year ago, we can see what Earth looked like because of all the satellites that are around our planet. We're constantly getting data about the weather and any of the cloud movement. And so everything you're going to see today is based off of where everything was in our universe yesterday afternoon. Actually, speaking of what is in our neighborhood, let's go ahead and look at our closest natural neighbor, and that is the moon. Now, I do say our closest natural neighbor, and it's as far as humans have traveled into space altogether. The Apollo astronauts came out here in the 1960s, and it took them 4 days to get to the moon. Now, even though the moon is close, well, our closest natural neighbor, it doesn't mean it's close in human terms. The moon is about 250,000 miles away from our planet. And as we go farther and farther out today, we are going to go distances of millions, billions and sometimes even trillions of miles. And when we get to these large distances, it doesn't make sense for us to use miles or kilometers as a measurement of distance anymore. So from here on out, I am going to use a different yardstick, so to speak, the speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is 2,000 miles per second, it would take us 1.5 seconds to get from Earth to the moon. So we say that the moon is 1.5 light seconds away from our planet. But let's go ahead and take a look at the surface of the moon. Now, the moon gives an illusion that it's been hit by asteroids, comets, meteors, more often than us, especially on the far side of the moon, which is what we're looking at right now. But the Earth is a much bigger target, so we actually get our fair share of impacts. The key is the moon has basically zero atmosphere, so there's no weathering and no erosion. There's also no plate tectonics that are moving around, so nothing is erased once those craters actually appear. But let's continue and zoom on out, and you may have noticed this kind of purplish line that's coming out from the moon. Well, that's not the moon's tail. That's actually just showing the path of the moon around our planet. Now, it takes the moon about a month to orbit around Earth, or I like to call it a month because it's not a full month. It's 29 and a half days. But let's go ahead and continue our journey. And as we head on out, I'm going to go ahead and bring up the paths of the other planets in our solar system. We can see the sun in the center. And if we count out those paths and label them, we would have Mercury closest to the sun, Venus, Earth, that third rock from the sun, Mars, and then even further out, we would have Jupiter, Saturn, Uranus. And we got to go a little bit further out to see Neptune's path as well. So these are the large planets in our solar system, where we have the rocky planets, or what we call terrestrial planets, in the inner parts of our solar system. We have Jupiter and Saturn, we call the gas giants, and Uranus and Neptune are icy giants. Now, this is where I get to show you a little bit of the back end of OpenSpace, which is a lot of fun, because I want to bring up one thing that looks like a kind of sizable gap in between Mars and Jupiter. So to do this, I need to bring up some small bodies, our asteroid belt. So each little dot shows where the path or where a object was, a asteroid in our asteroid belt is. And it looks pretty crowded. But remember, there's a lot of space in space, so there's great distances in between each one of these small bodies, including one object I'd like to talk a little bit more about. And its path is going to show up. It might be a little hard, but let's go ahead and zoom on in a little bit. It's a very light blue. We can see part of its path as we zoom on in. Now, any guesses of what this object might be in the asteroid belt? It's called Ceres. And Ceres has a very interesting story that I like to talk about. Ceres once was called an asteroid. And it was actually discovered a couple of hundred years ago, but now we actually call it a dwarf planet. I bet you have heard of another object that we call a dwarf planet in our solar system, Pluto. Now, the reason why I like to talk about Ceres and Pluto is because it's a story about how it's us who are naming things in space. So Ceres originally found about over 300 years ago was orbiting between Mars and Jupiter. Our technology wasn't as great as it is today, so we didn't know that there were a bunch of these little objects called asteroids. So we called Ceres a planet. As our technology got better and better, we started to see these small rocky objects. We called it an asteroid. And so Ceres became an asteroid. And this is what similarly happened with Pluto. When we were found Pluto, we actually were looking out and we didn't see much out here. Now let's go ahead and bring up Pluto's orbit. And as I mentioned, we thought it was the only thing out here in space. But again, as our technology got better and better, we were able to discover more and more things. So let's go ahead and turn on our trans-Neptunian objects, or TNOs. That's a lot of stuff out here in the outer parts of our universe, or sorry, solar system. So when we found all these small, rocky, icy objects, we realized that maybe Pluto isn't a planet in this specific type of category. So they try to create a better definition of what a planet is. And so they came up with 3 criteria for what is required to be called a planet. 1, it needs to orbit a star. Well, Ceres and Pluto do that, so check. 2, it needs to be large enough, massive enough to have its own self-gravity strong enough to pull itself into a round or spherical shape. All right, both Pluto and Ceres are pretty round, check. And 3, it needs to have cleared its path, meaning it needs a relatively clear orbit. Well, Ceres goes right through the asteroid belt and Pluto goes right through the Kuiper belt. They don't have clear orbits. So they decided that they needed a new category, so they became dwarf planets. Now, I know a lot of people were a little upset when Pluto got what some people say a demotion, but I like to think of this. Okay, so maybe Pluto got a demotion, but Ceres got a promotion. All right. Well, as you can see, my software is kind of getting a little slow because this is a lot of data. Each one of these markers represents a different either trans-Neptunian object or asteroid. And so it kind of slowed down my computer. So I'm actually going to go ahead and turn these off for now so we can explore the universe a little bit further. But let's recap on how far we've gone out into space so far. So remember that it takes 1.5 seconds to get to the moon at light speed. So we say it's 1.5 light seconds away. Now the sun is 8.5 light minutes away from planet Earth. And now if you would go from one side of Pluto's orbit all the way to the other, it would take 10 hours traveling the speed of light. So we say it's 10 light hours across. But let's go ahead and check in on our human influence. We've seen how far humans have traveled. Let's go ahead and see how far our spacecrafts have traveled. Now, these orange lines that seem to come away from Earth and out into various different directions are the paths of the fastest and farthest spacecrafts have gone. We have Voyager 1 and Voyager 2, Pioneer 10 and 11 that were sent out in the 1970s. And more recently, we have the New Horizons spacecraft that was sent out to Pluto in 2015. Now, these are the fastest and farthest spacecrafts, but none of them have traveled as far as light travels in a speed in a one light day. Pretty incredible to think about. All right. So as we zoom on out, you might notice there's kind of this haze that's happening, and that's because we had dimmed the sunlight so we can see everything, and we're starting to see the sun at its true luminosity compared to all the other stars. So we are going to start to fly past the other stars in our galaxy. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. So it would take us 4 years to get there traveling the speed of light. And even way out here, we can actually check in one more time on our human influence. This kind of grid sphere that I've just placed up onto our screen is what we call our radiosphere. This is as far as our radio and television signals have gone out into space, especially those first ones that were sent out in the 1930s. So again, if light's traveling the speed of light and radio waves are a type of light, that means this is a sphere that is 90 light years away from us in all directions. So let's go ahead and also check in on how many planets we have found outside of our solar system. Now, these rings are around individual stars that have at least one exoplanet or planet outside of our solar system around it. We have found thousands of exoplanets so far. And if you carefully look, there are several planets inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole. That'd be pretty neat. But let's keep on going. We still have a lot of space to travel because we are still flying past the stars that are in our own galaxy. We haven't even gone outside the Milky Way yet. And as I zoom on out, I encourage you to keep an eye on that radiosphere. See how long it takes for you to maybe lose it, or you've been able to find it the whole time. Now we're going to start to see the large scale structure of our galaxy, the Milky Way. We live in what we call a spiral galaxy. It's pretty flat actually. And we have these beautiful spiral arms that are made of gas and dust and stars. And in those spiral arms, about 2/3 from the center, right in the center, we would actually be a big group of stars. And if we could see those big group of stars, we'd actually see a supermassive black hole. Well, we wouldn't actually see the black hole, but we see evidence of it. And that black hole is about 4 million times the mass of our sun. Now, I think I might have skipped a point. Sorry about that, but we live 2/3 of the way out from the center of our galaxy. Does everybody still see the radiosphere? If you do, go ahead and point towards it. You're all correct because I have no idea where you're all pointing. But if you try and put your 2 fingers up, it's about looking at our galaxy 5 o'clock, you would actually see the radiosphere. And that's our little area in which we live in our galaxy. Now, from one side of our galaxy to the other, it's about 100,000 light years across. So we are now at distances of thousands of light years. And our galaxy has roughly about 4 billion stars in it. But it's just one of the many galaxies out here in our universe. Every dot we see is now not a star, but another galaxy with its own billions and sometimes trillions of stars. And the colors of these galaxies may make it seem like somebody accidentally spilled some cosmic Skittles in the universe, but these aren't the actual colors of the galaxies. It just shows us the different surveys that mapped these galaxies. And as we zoom out even further, we can actually start to see some interesting effects of how we map our universe. You may notice maybe our universe looks like a bow tie or a butterfly. That'd be pretty cool, but it's not actually that. Again, it's how we're mapping our universe. Everything we see is based off of the data that we are collecting from our telescopes, and we're all looking out. And you may notice there's some pretty big gaps in our data. And that's because remember when I was talking about our galaxy, how it's made of gas and dust and stars? Well, that gas and dust actually blocks our view. So we can't see past our own galaxy. And so we haven't mapped these areas. And because we haven't mapped these areas, that's why they look blank. Remember I told you that OpenSpace is taking live data as well as what we have mapped. This is all real. So we're not going to show you something that we haven't mapped yet. You also might notice that it looks like we are the center of the universe. Well, as far as we know, there is no center of the universe. And again, it's because we are creating this map. It's from our perspective. We look anywhere, it's going to look like everything's around us. If we were to go to any one of these other galaxies, maybe in the upper right-hand corner or maybe towards the bottom of our screen, all of those, if we were in those places and we were making the map of the universe, it would look like we were the center as well. Again, we're pretty sure that there is no center of the universe. All right, we still have a little bit to go. I know it feels like we've been traveling a long time. And now we're at billions of light years away. In fact, these kind of red dots that are starting to appear on our screen are some of the oldest things in our universe and some of the earliest objects in our universe. They're called quasars. They're bright cores of some of the first galaxies. And I actually do mean earliest because anything that we are looking at out into space, we're kind of time traveling in a way. The light of those objects has to travel so far that by the time it travels all that distance and gets into our telescopes, we're actually seeing those objects as they were in the past, not how they look today. So, for example, remember we were talking about the closest stars to us about 4 light years away from us? That's how they looked 4 years ago, not how they looks today. And as I said, now we're looking at our universe billions of years ago. And because of that, that means there's only so far we can go. There's an edge to everything we can see. And we can now see that edge. Kind of looks like splotchy red and dark marks on our screen. And this is what we call the cosmic microwave background, or CMB. Now, if you had a radio telescope and you could see in the microwave range of light, you would actually see this everywhere you looked in the sky. In fact, the first radio astronomers were very confused of what they were looking at. But they realized that it was actually something they were seeing out in space. And this is what a few hundred years after the Big Bang would have happened. They're temperature fluctuations. So where it's very dark is kind of the cooler regions, where it's very bright is going to be the hotter regions. And when I say between hot and cold, these are fractions of a degree. So we can actually think of the cosmic microwave background as our baby picture of the universe. And because this is our baby picture, this is as far as we can go. We can't see any further. So it's time to start to head back home. Now, if we were actually that far out in space and we were actually flying the speed of light, it would take us 13.7 billion years to get back home. But thankfully, with the power of our planetarium software, it's going to be taking only about a minute. But one more thing as we zoom on back home. All of this that we looked at today, all these stars and galaxies and the cosmic microwave background, that's not everything in the universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. There's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call all of these things dark energy and dark matter because, well, we're not quite sure what they are yet. But we do know that they make up about 96% of our universe. So everything we've seen so far is only about 4% of everything that is out there. And that might make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we are one tiny dot, but look at all that we have found so far, almost entirely by looking through telescopes. And there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what it makes it a wonderful time in our human history. Is that we're not able to just learn about these things, but show them a map of the cosmos in 3 dimensions. And we're starting to finally unravel the true nature of our universe. But we're only starting to unravel. The rest, well, it's up to the next generation of scientists back here on planet Earth. Well, here we are, everybody. That third rock from the sun, the only place in all of this that we have found life. And that's pretty incredible to think about. So I want to say thank you, everybody, for joining me here. And I hope you have a great rest of your day. If you'd like to learn more about OpenSpace, we're going to go ahead and place a link in our chat box, as well as we would love to hear what you think about this program and any other programs that we provide on our OpenSpace software. Well, thank you, everybody, and I hope you have a great rest of your day.